In the last video, I said that flash combustion can tell us the ratio of the elements in a compound, its empirical formula, but not its molecular formula or how the atoms connect. But why is that? Well, it's because we're not actually measuring the molecule in the sample itself. We're measuring the products it produces through a combustion reaction. For organic molecules like diphosgene, that means we burn the molecule completely in excess oxygen, so that every carbon generates one carbon dioxide, every two hydrogens creates one water molecule, every two nitrogens create one nitrogen gas molecule, two chlorines produce one chlorine gas molecule, and so on. Since we're adding excess oxygen into the reaction, what this method can't measure directly is the number of oxygens in the starting material. To find that, we subtract the masses of all the other detected elements away from the initial mass. Any difference that isn't accounted for by the combustion products has to be the mass of oxygen. Let's see how this works in a fictional scenario. During an unrelated arrest, the RCMP discover what looks to be an improvised lab space. Not knowing its purpose, they request support from the Canadian Joint Incident Response Unit. CJIRU's CBRN techs secure and clear the lab, taking samples of any chemicals found, including the remnants of a clear, colorless liquid in an unlabeled jug of 1 liter. Burning a 3-gram sample of the unknown compound in excess oxygen produced 4.397 grams of carbon dioxide and 1.800 grams of water. First, we want to determine its empirical formula. To do this, first we want to determine the number of moles of carbon dioxide produced. That means dividing the mass of carbon dioxide by its molar mass to get 9.991 times 10 to the negative 2 moles. From that, we can get the number of moles of carbon that were on the original sample. There's 1 carbon for every carbon dioxide molecule, so we have the same number of moles, 9.991 times 10 to the negative 2 moles of carbon. We want to do the same thing for water. So that's 1.800 grams divided by water's molecular mass gives us 9.992 times 10 to the negative 2 moles of water. To determine the number of moles of hydrogen, we convert the moles of water into moles of hydrogen by saying there are 2 moles of hydrogen for every 1 mole of water. And that gives us 1.998 times 10 to the negative 1 moles of hydrogen. To find how much oxygen was attached to the original compound, we need to subtract the weight of the carbon and the hydrogen from the weight of the initial sample. So we multiply the moles of carbon and the moles of hydrogen by their molar masses to determine the mass of carbon and the mass of hydrogen. Those we subtract from the original sample mass to determine the mass of oxygen that must have been on the original sample, 1.5976 grams of oxygen. That again, we can use the atomic mass to convert into moles, and we come up with 9.985 times 10 to the negative 2 moles per oxygen. So to use that information to get the empirical formula, we need to convert these numbers into small whole number ratios. And we get that by dividing the moles of each of these components by the smallest number, which gives us pretty close to 1 for carbon, and 1 for oxygen, and 2 for hydrogen. So our result, the empirical formula of the unknown compound, is CH2O. Further physical and chemical testing of things like boiling point, viscosity, vapor pressure, confirm that the unknown liquid is methyl methanoate. This material is a precursor for a wide array of reactions, but the presence of a cylinder of chlorine gas and a UV reaction chamber, and not to mention the covert nature of the lab itself, narrows down the possibilities. We're going to continue this scenario in the next video.